Hi, good evening, everyone. So, yes, I'm going to talk about a particular ocean, and I'm going to give some indications of the role that mathematics plays in understanding that ocean. But in general, oceans are our friends. They suck in carbon, they give out oxygen, they help our planet to breathe. They also soak up about 90% of the excess heat that we create by burning fossil fuels. That's my fault. Okay, so imagine that I asked you, how many oceans are there on Earth? And imagine you were being clever and a little bit funny. And you said, there's just one, because all of the identified oceans are interconnected. Well, I would say to you that that is a bad answer. It is a static, flat world view which overlooks fundamental differences between the major water bodies. Instead, we need to take a dynamic, three-dimensional view of the oceans in order to appreciate their differences. And it is important to recognize those differences for public awareness of the way our planet works, of climate change, of science, and of the mathematics that underpins it all. I'm going to talk about the Southern Ocean. It's an uninterrupted oceanic ring that sits beneath all of the continents inhabited by humans. It connects almost all of the major oceans to the north, and it's the gateway to the Antarctic to the south. I live in Adelaide, and the Great Southern Ocean is on my doorstep. But it has influence over the entire planet. It's fine to refer to it as the Antarctic Ocean, so long as you don't confuse it with the Arctic Ocean, because the Southern Ocean is very different from the Arctic Ocean. In fact, the Southern Ocean is like no other ocean. It's working harder than any other ocean to counteract climate change. So when I say that the Southern Ocean is hardworking, what I'm talking about is the continual movement of water masses around it. And that's in both the horizontal and vertical directions. And that movement brings up cold water from deep down to the ocean surface, moves it north where it's heated, and it's then moved back down deep again. Now, that process is driven in part by the strongest winds on Earth, which exist over the Southern Ocean. Those winds, they blow across the ocean surface without any land there to slow them down. And they generate the largest waves on the planet, which are up to 20 meters in height. That's a 5-story building. Now, this harsh, dynamic, windy and wavy ocean is why sailors refer to the roaring 40s, furious 50s, and shrieking 60s. Another reason that the Southern Ocean is special is because it's where the cold waters from the south meet the warm waters from the north. And they meet in the strongest, fastest current on our planet, which is known as the Antarctic Circumpolar Current, or ACC. The ACC wraps all the way around the Southern Ocean. And it stretches many kilometers from the ocean surface to the seafloor. And it's pumping water around the Southern Ocean rapidly. And in doing so, it's redistributing heat, fresh water, and carbon dioxide to all of the other major oceans to the north. The ACC also plays an important role in protecting the icy Antarctic to the south from warm waters. So that includes the Antarctic ice sheet, which is by far the greatest store of fresh water on our planet, and by far the greatest threat to global sea level rise. The Southern Ocean comes into contact with the Antarctic ice sheet through ice shelves. They are the giant floating extensions of the ice sheet. And then there's the frozen surface of the ocean surrounding Antarctica, which is known as sea ice. Antarctic sea ice plays an important role by reflecting the sun's rays to keep the Southern Ocean cool. It's a really important component of the Southern Ocean system. It expands and contracts with the seasons. In winter, it doubles the size of the polar ice cap. Now for the bad news. Southern Ocean is changing. It's warming, and that is having knock-on effects, such as record Antarctic sea ice lows and losses of major ice shelves. It's not clear how much longer the Southern Ocean can go on playing its critical role in the climate system. And the raw physics is straightforward. We keep on pumping carbon into the atmosphere, the oceans keep on warming, sea ice goes, ice shelves collapse, and then the Antarctic ice sheet melts into the Southern Ocean. But the details of how and when this might all play out, and also the possibility of it all being reversible, is fiendishly difficult. It requires that we understand the feedbacks between the different components of the Southern Ocean. So we have three main tools in order to understand the Southern Ocean and to make predictions. We have theory, we have observations, and we have numerical models. Mathematics underpins each of these three tools. So theory involves turning physics into mathematical equations. Mathematical algorithms are needed to turn observations into data. And numerical models are based on mathematical methods and approximations. Real advances, come from using theory, observations, and numerical models together. I'm going to spend the rest of my talk giving you three examples from Southern Ocean science. My first example is the phenomenon of ocean waves breaking up continuous sea ice covers into small chunks of sea ice known as ice flows. Those ice flows melt far more rapidly than continuous ice covers. Now, what I'm showing you here is what I think is a fantastic recent observation of the phenomenon. It was taken by a drone. From this, we can extract properties like ice flow sizes. We can analyze their statistical properties. Now, In the interests of complete transparency, that observation comes from an estuary in Quebec. And for any of you out there with sharp eyes, yes, the waves in this case were generated by a ship passing by the ice. But I think it's a really exciting example of the sort of observations that we might get in the Southern Ocean in the future as drones and other technologies mature. And we're developing associated theories. They require us to couple together two existing, very different theories, one for water waves, the other for sea ice. And we started integrating those coupled theories into numerical models to make predictions that can be verified by the observations. I'm going to motivate my second example using a short movie which was generated using outputs from a high-resolution ocean model, a numerical model. We'll start at the ocean surface with properties like the sea surface temperature and the sea ice coverage. Now, the real power of the model is that it allows us to pull back, strip away the surface layer of the ocean and look deep into the Southern Ocean to see what's going on. And there we find waterfalls of cold, dense water plummeting kilometers over the edge of the Antarctic continental shelf. And also underwater waves, hundreds of meters high. Amazingly, we're also making observations deep under the ocean surface. We use thermometers attached to bobbing robots, known as Argo floats. They dive kilometers beneath the ocean surface to make observations. They then return to the surface to relay data to satellites. Developing mathematical theories for such a complex system as a three-dimensional ocean is, quite frankly, intimidating. Now, one trick that is commonly used is to treat the ocean as a stack of water layers where each layer has uniform properties. And that sort of theory can make predictions, for example, how the Antarctic circumpolar current interacts with mountains and cliffs on the seafloor to send cold bottom water up to the ocean surface in a process called upwelling. Now we're going to travel to the Thwaites Glacier, nicknamed the Doomsday Glacier, as it's considered to be the greatest threat to sea level rise over the next decade. That's because the base of the ice shelf that it's attached to is thinning rapidly. And its so-called grounding line is retreating. In order to make observations of this, a team of scientists recently drilled through over 500 meters of ice above the grounding line. And they deployed an underwater robot through that in the water cavity beneath the shelf in order to observe the ice shelf base, where they found features which they called terraces, which give some clues about the melting processes going on there. Melts of the ice base can't be predicted simply from knowing the ocean temperature. We need to know about how both heat and salt are moved between the ice and the water. And the controlling processes are too small and fast to be captured by numerical models on the scale of an ice shelf. So we need theories such as for so-called diffusive staircase structures of water layers beneath ice shelves, which control melt rates. We can then feed these theories into numerical models and make predictions. However, this theory and those in the previous examples that I've given, they're not standard in predictions given by, for example, climate models. There are lots of tests, validations, and calibrations that are needed. Okay, well, I hope in this relatively short talk that I've given you some ideas about why the Southern Ocean is crucial to our planet. And I also hope that I've given some explanations of why mathematics is so important to understand the Southern Ocean and to predict its future. Thank you.